Welcome everyone, and thank you, Michele, for the introduction. I'd like to thank the organizers, Michele, Andrea from PBL and EFCL, who've done a lot of work to organize it. I'd like to thank all the speakers for coming here also. So hopefully I'll be able to see you by the end of this talk. There's some light shining at me over here, but yeah, hopefully we will do it without wearing sunglasses. Okay, so I'm going to talk about memory-centric computing today. The topic of the workshop is sustainable AI. And I think if we want to talk about sustainability, we should really scrap what we're doing in our computing systems today and rethink everything from a sustainability and energy perspective. Without doing that, I think we should not think about sustainability. And hopefully I will convince you that what we're doing in our computing systems today, from the very beginning, fundamental principles are wrong for energy and sustainability. If you sleep there for the rest of this talk, hopefully you'll get away with that. So I think today computing is bottlenecked by data. Data is really key for many applications. AI, machine learning, genomics, databases, many other applications are data intensive. They require rapid and efficient processing of large amounts of data. And data is increasing on top of this. We're basically generating a lot more data than we can process today. In fact, it's a bit crazy in the sense that we're generating synthetic data to train machine learning models, which may be good or bad, but data is really multiplying in an unprecedented amount speed. And we need to perform more sophisticated analysis on more data. So this is one example. I will not harp on this a lot, but clearly model memory requirements are growing for machine learning models, and compute requirements are also growing. Let me see if I can make this work. Yeah, this is memory requirement, this is compute requirements. And essentially, we want more memory and more computation close to each other. And some people are doing innovative work to actually try to bridge this gap. These folks, for example, from Cerebras are building wafer scale chips that are this large as a potential solution. I'm not sure if that's a great solution because it doesn't put a whole lot of high density memory close to high-density compute. It's low-density memory, high-density compute, perhaps, which may not be good for all cases. But anyway, we can talk more about that. But that's one application is machine learning. Another application is genomics. We do a lot of work in this area. And this is an area where data is really growing much faster, in my opinion, because we can actually generate, we have technologies that can generate data much faster. I can talk about applications, but let's switch to what do we really want. What is sustainability? Sustainability, in my opinion, is livability and also being efficient in cost, energy. There are many metrics associated with it. In my opinion, it kind of boils down to, do we want a world that looks like this, where we are comfortable living in, or do we want a world where we cannot breathe and we cannot live in for a few more days, maybe? I think human beings are greedy. We want a lot of things at the same time. We want high performance, energy efficiency, and sustainability, and we don't want to give up anything. And I think this is a good mindset going into the future because clearly we have a lot of problems to solve which require high performance. But high performance should not come at the expense of energy or sustainability. We really want to maximize all three metrics at the same time. So the problem is when we design our computers fundamentally, we're causing a lot of issues that go against all of those three metrics. Essentially, we're accessing data which is far away from the computation units. And we're wasting a lot of energy to move the data to the computation unit. Wherever your computation unit may be, it's usually far away from where the data is generated or stored. And this energy waste gets multiplied because we also make our systems very complex to tolerate the performance loss that happens due to the data movement. We actually add a lot of complexity to our systems, as I will show you in the next few slides. We have huge cache and memory hierarchies, which occupy a lot of area, which is a key cost in sustainability. We have many prefetchers. We have many levels of multi-threading. We have huge out-of-order execution engines. And that's just at the hardware level. So at the software level, we complicate our software even more to actually overcome the data movement bottleneck. And when sometimes these techniques work, but many times these techniques don't work or don't work completely. And when they don't work, they actually compound the energy waste because now there's a huge added complexity to our system that actually increases the latency and also increase the energy consumption. So we're in this vicious cycle because we are not treating data access properly, in my opinion. We're moving data a lot in our system. We're causing performance loss and we're causing energy waste, and we're multiplying that energy waste by trying to overcome the performance loss that comes from that data movement. So the fundamental problem is really today's computing systems are processor-centric. All data has to go through the processor And this comes at great system cost. So this is my cartoonish picture of a modern computing system. It hasn't changed that much. This is a picture from 2008. And if you look at it here, there are some processing elements, cores over here. It could be accelerators. But most of the system is really dedicated to storing and moving data. Everything else, other than the computing units, which are a very small fraction, as you will see soon, are caches, interconnects, other interconnects, buffers, memory controllers, other interconnects, memory, and other interconnects, and storage, and other interconnects, etc. So if you take this picture and show it to someone and say, okay, I'm dedicating almost all my resources, more than 95% of a single node in general, to storing and moving data, what do you think is the bottleneck in the system? A good engineer would probably tell you that if you're dedicating all of your resources to it, hopefully that's not a bottleneck, right? But unfortunately, we're still bottlenecked by memory. Okay, you don't like my picture? This is AMD's picture. It's a real chip. And the green part is just L2 and L3 caches over here. And then there's a lot of other stuff like global memory interconnect, etc. If you don't like that picture, AMD is adding more and more caches. It's actually great technology, 3D stacking technology, so that you can actually stack things on top of each other, which I'm going to talk about in a different way. But we're using it as caches in some of the mainstream processors because we're very processor-centric. Okay, this is IBM, another picture over here, green. This is some other company, another picture. I look at this chiplet-based processor as a lot of SRAM. A very small fraction of this chip is dedicated to do processing. And the rest of the system, a lot of DRAM, does nothing except for obeying what the processor says and moving the data over there. And there's a starkness that everybody forgets about, which is the storage. Okay, so let me give you some performance very quickly. Clearly, we have known that memory is a problem, and we've tried to overcome this problem. This is one of my favorite papers from Dick Seitz, who was the chief architect of alpha processors, which were the fastest processors of their time in 1990s. After their team designed one of the fastest processors of its time, Dick Seitz wrote this one-page paper saying that we designed this beautiful processor. It's capable of finishing 4 alpha instructions every clock cycle, which was one of the fastest of its time in 1990s. Unfortunately, on this important database workload that we think we optimized this processor for, it's finishing 1 instruction every 4.7 clock cycles. So it's operating at around 5% of its efficiency, even though most of the chip is still dedicated to store and move data with lots of caches, interconnects, etc. So if you think about that, that's about 5% efficiency. We'll get back to that. And he finishes the article saying that I expect that over the coming decade, memory subsystem design will be the only important design issue for microprocessors. Okay, this is data from my own PhD thesis. With Intel, we did a lot of studies to understand the bottlenecks in processors and to design better processors at the time. And we found that essentially the same thing. Most of the time, the processor is waiting for data to come back from memory. And we proposed some solutions that I'm not going to talk about. But let's fast forward about 10 more years. This is Google's data in 2015. They basically profiled all of their data center applications, and in a state-of-the-art processor, they found out essentially the same thing. Most of the time, the processor is waiting for data to come back from memory. It's really doing what it's supposed to do, which is finishing instructions only 10 to 20% of the time. Again, it's good to ask the question. I think most people here are engineers or scientists. As a good engineer, does it really make sense to design something that is doing what it's supposed to do only 10% of the time, or 10 to 20% of the time? That efficiency is very low. Okay, so that was performance. Let's talk about energy very quickly. Energy is even worse, basically. If you look at energy, a memory access is much more expensive than a complicated arithmetic operation. Sorry, this is a bit slow. I don't know why. This is data borrowed from Bill Daly. This old data. You can argue with all of these numbers over here because things have changed. You can optimize things. But what remains is a memory access is still about 2 orders of magnitude more energy costly than a complicated arithmetic operation. Okay. And if you make the arithmetic operation less complicated, which is in this case a 32-bit integer operation addition over here, that disparity increases, basically 6400x. Now it's good to ask the question. I'm going to add 2 numbers. Does it really make sense for me to do 2 memory accesses to get the 2 operands, bring the data into the cache, and then into the register file, actually, not just the cache, through the cache hierarchy, all the register file, and then do the operation and then write back the data to memory again. That's 3 times 6400x. And this is an optimization problem. Of course, sometimes it makes sense, right? If you can actually exploit the locality in the program such that you can reuse that data many, many times to amortize the energy cost, yes, it makes sense. The question is, how often do you need to reuse that data? You can make the calculations, that's a huge number, essentially, and many workloads do not have that huge number of reuse of elements to amortize the energy costs. So this energy actually becomes worse if you think about it. Today, we're trying to do machine learning with smaller bit widths, 4 bits, 8 bits, hopefully 1 bit at some point. That'd be great, I think, because for efficiency. And if you think about that, this disparity increases as you reduce the bit width. And we're not even talking about storage yet. This is still DRAM. If you think about storage, add one more order of magnitude over there. So the numbers go a bit crazy. It gets closer to 100,000x or so. And this is all hidden from us. If you think about it, we designed the systems this way, and we're wasting this energy, but we don't know about it because the system is designed that way. Its cost has already been amortized over time, except we see this cost in energy and sustainability, in my opinion, because the system has been made very complex to try to tolerate these. Okay, so we did a lot of studies to understand the implications of this on performance, this data moment on performance as well as energy. This is one study. We've shown on important mobile workloads like machine learning inference and TensorFlow or video processing, Chrome browsing. We found out that more than 60% of the total system energy is spent on data moment on average use cases. That's relatively old. We also repeated this sort of study with Google on edge machine learning accelerators that are actually specifically designed for accelerating machine learning on the edge, on the device. And we found out that on large machine learning models, more than 90% of the total system energy is spent on memory. Hopefully, I'll get the time to actually discuss how to design better machine learning accelerators soon. But just to give you a foreshadowing, these are some, at the time, models that were large, used in Google Edge devices, LSTMs and transducers. You can see that in baseline systems, most of the energy is really spent on DRAM and the interconnect. And high bandwidth memory reduces it a little bit, but doing processing near memory reduces it a lot more, about 5x compared to the baseline. We're going to talk about that, but I just want to give you as a foreshadowing of what's happening. So basically, the fundamental problem is we're processing data far away from the data. We have to move the data all the way to the processor through a huge hierarchy to enable processing. I believe we need to change that. We need to enable computation with minimal data movement. We need to compute where it makes sense. And we need to enable computation everywhere. We have a lot of places to do computation. We're restricting ourselves to a very small fraction of an SRAM-dominated chip today. Whether it's a machine learning accelerator or a CPU or a GPU, it's still an SRAM-dominated chip in the end. We want to compute where data resides, and essentially we want to make computing architectures much more data-centric as opposed to processor-centric. So these are some places where we can do computation, right? I want computation everywhere in that darkness, let's say, as opposed to this single chip or chiplet. Okay, so I don't know what happened here, but sorry. Okay, there you go. So we're going to treat memory as an accelerator, essentially. We have been designing a lot of accelerators. We've figured out that this is not good for the processor-centric paradigm. So if you have a single type of processing unit, we figured out that that's not very efficient. So let's actually design accelerators that cater to different types of applications. And we've been doing that for a long time. This is clearly heterogeneity on the processor-centric domain. Why not have some more heterogeneity that's also more data-centric? That's the idea. I'm trying to get used to how this works, but maybe I'll use my hand over here. That may be easier. Essentially, we would like to do computation on the other side of the memory bus, if you will. Okay, so there are a lot of questions over here, and this is a big area. And I'm going to focus on processing in memory and storage, but clearly you can do processing near or inside the sensors, on the interconnect, in the SRAM, in the processor chip. I believe everything should be enabled so that we can actually figure out where to do the computation most efficiently and most sustainably. So what are the questions? Essentially, we would like to design, how do we design the compute-capable memory and the controllers? How do you design the processor and communication units? And how do you rethink the processor once we actually have computation capability everywhere else? Maybe it'll be much more leaner, specialized for extremely, let's say, I don't want to say rare, but relatively extremely compute-intensive tasks, as opposed to data-intensive. How do you design the software and hardware interface to enable this? How do you design the system software compilers and languages so that we can make it amenable to many programmers in the world? And how do you rethink the algorithm so that we can actually match the computation capability in the hardware? I will also mention theoretical foundations over here. We're in the computer science building. A lot of people may be working on computer theory. If you think about that theory, it's all processor-centric. So we have not developed a theory that is really data-centric. I believe we really need to do that going into the future. What do we do in a theory of computation today? We count operations to determine algorithmic complexity. But maybe that's not that important in the data-centric domain. If data is what's limiting you, maybe we should be doing something else in theory. Okay, so it's really an across-the-stack problem, which is very interesting and exciting, and I'm going to show you some example problems as we go through this talk. But I should also say that this is not a new idea. This idea has been proposed. We're not the first ones. We're actually probably maybe in the thousands or so who have looked at this problem. In the 1960s, these are some of the oldest papers that I could find that talk about logic in memory. I'm going to use their terminology, saying processing in memory in general. This is a particular type of processing in memory, which puts logic close to memory. Even though they say logic in memory, it's really logic near memory, if you will. And there's another beautiful paper from Harold Stone that talks about this, if you're interested. If you find some other paper, please let me know. So you may ask, people have tried this for a long time. Why is it interesting today? Basically, I think today we have nowhere to escape. In 1960s, we had somewhere to escape. Today, basically, as I showed you, our applications and systems are forcing us to do something different. If we want to improve both performance, energy, and sustainability, I believe we can improve all metrics by minimizing data movement. And also, we're having huge problems with memory technology. I'm going to talk about this relatively quickly, because I think this is going to get much, much worse into the future, especially in large technologies that are dominant today, DRAM specifically, but also flash going into the future. I'm not going to talk about SRAM as much. It's important, but it's going to also have scaling issues going into the future. And then there are emerging memory technologies that are trying to emerge to overcome some of these problems, but they also have their own problems as they scale going into the future. Essentially, technology scaling is not going well. And to overcome technology scaling issues, we actually want computation or intelligence near memory in general. This is true for, I think, all memory technologies. If you look at flash, for example, it doesn't work off the bat. There are a lot of issues with flash memory. So you really want some controller to overcome the downsides and control flash memory. So there's a lot of intelligence that's embedded into the flash memory technology today, actually, if you think about the flash subsystem. We're having the same issues in DRAM, in my opinion. And also, I think emerging memory technologies can solve some of those issues, but they also have their own issues. But they can also enable new functions in memory, as some folks like Abu is going to talk about that later on today, I think. Basically, today we're kind of squeezed in the middle. At the top, applications and systems are pushing us to do something different, which is fix the data movement problem fundamentally. At the bottom, memory technology is not scaling. As a result, it's saying that, oh, you should do something else so that you can save me, you can scale me. So that requires intelligence in memory also. Let me give you an example of this intelligence. We've been working on technology scaling quite a bit in different domains, but essentially, one example is the RowHammer problem. This is a technology scaling problem. And this is because the technology, DRAM technology, has scaled so much, cells have become smaller and cells became too close to each other. As a result, when you access one row, you disturb adjacent rows. And as a result of this, you can predictably induce bit flips in commodity DRAM chips. Essentially, all DRAM chips are vulnerable. And this has implications on robustness, clearly. You have data corruption, you have reliability issues, you have safety issues because of that, but you also have security issues. In fact, this is, in my opinion, the first example of how a simple hardware failure mechanism can create a widespread system security vulnerability. People have done a lot of interesting work in this, and I like this paper. I keep showing this over here, but it says, forget software, now hackers are exploiting physics. This is a nice mindset, I think. It's good that people are actually going to the lower levels to understand what's going on. Okay, so what is RowHammer? Very quickly, in memory, you have a bunch of rows, and if you activate one row, you can read data from that row after that. This activation requires applying high voltage to the word line. After that, if you want to read some other row, you apply low voltage. Now, if you keep doing this repeatedly, high voltage, low voltage, high voltage, low voltage, activate, precharge, activate, precharge, activate, precharge, in modern DRAM, it turns out some physically vulnerable cells in physically adjacent rows get flipped. They lose their charge, little by little, with every activation. And if you can do those enough activations before the cells get refreshed, you can deplete the charge, and as a result, you can cause bit flips. Clearly, this should not be happening. We call this hammered row, we call this the victim row, and we show that you can induce bit flips, you can induce bit flips essentially in all DRAM chips today by doing this. So this is clearly very interesting. I can have a talk about that, but I'm not going to do that. But this is a technology scaling problem. So this problem becomes worse with technology scaling. When we did our initial studies in 2013, the number of activations to induce a bit flip was around 140,000. Over time, it got reduced by 10x and then another 10x with another technique that I will call row press. Essentially, today you can induce bit flips with 100 activations or so. And we have a paper coming up that shows that it's actually even worse soon in HPCA 2025. So the reason is cells are closer to each other and cells are much smaller, so it's very easy that whenever you access one cell, you're affecting other cells around it. Okay, so there are a lot of papers on this topic. I'm not going to talk about it. And there are a lot of security papers on this topic also, not just testing and understanding papers, but people have shown that you can exploit these bit flips to take over a system, use a user-level program. You can read data that you do not have access to because you can flip bits and understand the relationship of those bits to other bits around it. You can break out of virtual machine sandboxes. You can corrupt important data, and you can render machine learning inference useless, essentially. People have shown that by targeting these bit flips in particular weights in machine learning systems, you can actually lower the accuracy of machine learning inference greatly. And also, people have shown that you can steal secret data. For example, you can steal cryptographic keys and machine learning model parameters that you may consider secret. Okay, so this is interesting, and there could be a lot of interesting things. I'll just leave the RowHammer with this. Essentially, a very famous hacker on the internet said, RowHammer is like breaking into an apartment by repeatedly slamming a neighbor's door until the vibrations open the door you were after. So it's interesting. So how do you solve it? Essentially, the solution requires intelligence in memory. There are a lot of papers, as I show over here. Essentially, you can read more about it, but solutions require intelligence in memory, and we've argued that for a long time. And it's not just about RowHammer, it's about other technology scaling problems. For example, refresh in DRAM. If you want to get rid of the refresh problem, you need an intelligent memory controller. We've argued this for a while. I'm not going to bore you with the arguments, but after about 10 years or so, industry has adopted, I think, this solution in a kind of interesting way. This is a paper from SK Hynix and ISSCC in 2023, where they talk about RowHammer, etc. And they basically say, we solve this problem by putting intelligence in our DRAM chips. This intelligence comes at an expense. It's costly, but they have counters for each row. This is called per row activation counting in the recent incarnation. And whenever you access one row, you increment the counters in some way. And if the counter is greater than some threshold that is not disclosed as much, you do some mitigating actions so that hopefully RowHammer bit flips don't happen. So I would say that this is an intelligent controller that actually maintains a lot of metadata. This is a good, in my opinion, this is a step in the right direction. It may not be the best solution to RowHammer, but JEDEC actually is standardizing it. They recently released the DDR5 standard that standardized it. So there's a lot of interesting thing going on. It's good to think about our solutions good. So this is a solution so that you don't go over that fence, but you can also bypass that fence, right? So it's good to think about how to solve this problem. So we recently shown that this problem is much worse. If you keep the row active, you can actually induce much more bit flips. So these things will come, and the controllers on the technology side will become more and more intelligent. So for example, this is a very recent PhD thesis from one of my PhD students, Giray, that shows that if you make the controller even more intelligent, you can solve this problem much better. But I'm not going to talk about that in detail. So, but I will say that there's more to come in technology scaling that will require us, especially in DRAM, and increasingly in Flash also going forward, although Flash is pretty intelligent today, but there needs to be more intelligence on those sides. So that was a technology push. You can say that, you're talking about DRAM, which is not an interesting technology maybe for some of you, but I would argue, I would push back otherwise, because I think DRAM is going to be with us for a really long time, in my opinion. Maybe it'll change in its type a little bit. It may become three-dimensional, etc. But other emerging technologies are also very interesting, and I like working on those topics. It's exciting. But they all have their own problems as well, like endurance. And they need intelligent controllers for those reasons. And when they scale to smaller technology nodes, I believe any technology has similar issues, like read disturbance, write disturbance, etc. And you really need intelligence on the memory side. Okay, I kind of took some time to talk about this part over here, because I think this part is kind of not discussed as much, especially in system level papers, but I think it's important to recognize that we're putting intelligence in memory already. Then the question is, why not put more intelligence in memory to do computation? You already have computation capability inside the DRAM chips to increment these row activation counters, and there's more actually being added for testing, etc. So why not actually extend it? Okay, any questions so far? Maybe I'll get some water over here. I can take questions afterwards too. Now let's go into how we can do processing in memory. I think there are two approaches to processing in memory. One is processing near memory, and there is processing using memory. I think these are two fundamental approaches. If you find another approach, let me know. I'm going to talk about processing near memory first, because I think this is easier to adopt in industry. And then I'm going to talk about processing using memory, which is more analog type of computation, which is harder to adopt. But I think in the end, if you really want to be extremely efficient, we want both to be happening in our systems, and we want to combine them. So what is processing near memory? It's essentially what we're doing today. We have a processor, and then we have memory. There's some distance between them. We could make that distance farther, which is probably a bad idea. We could make that distance closer and closer and closer and put logic very close to memory, inside the memory, near each bank, etc. Basically, get the integration much better. But we design logic and memory, or processor and memory, separately, as we do today. We don't change that paradigm. And we know how to do both, I think, today. Processing using memory is fundamentally different. You basically have logic or processor and memory, and you forget about the logic for some time, and you say, I have just memory. Let me think about that memory, and let me understand its analog operational properties to do computation. And I think this is very exciting. This is more recent. This was not envisioned in 1960s as much, let's say. At least we don't have papers on this topic. And this is fundamentally much more efficient because it's analog computation. And it can enable more efficiency, but it's probably more restricted in its usage, at least initially, until we really understand how to exploit this paradigm. But going forward, I believe we need a combination of both. So let me start with the first one, which is already happening, in my opinion, processing near memory. Essentially, this is a picture that is getting populated more and more. We have technologies that look like this. We have 3D stacking that I'm going to talk about. It's going to get better and better over time. We'll have a logic layer underneath memory layers, and logic layer would be high quality. We can do computation in that logic layer. More recently, people have also devised memory chips that have processing units next to each bank. The UPMEM processor is essentially a general purpose processor, but there are also more special purpose machine learning accelerator type of processors that are added to DRAM by Samsung, SK Hynix, and Alibaba. And people are also experimenting with buffer chips that can actually aggregate data and do computation for recommendation systems, for example. And there are many, many other chips, experimental chips and startups, some of which you may hear about later today, that are not in this picture yet. All of them, I think, are doing processing near memory, at least a great majority of them, because this is easier to do in today's technology. And also, I think the opportunities are growing. Essentially, people are adding interfaces like Compute Express Link that enable offloading of computation to somewhere else other than the processor and accelerator more easily. And I think this is a good enabler of doing computation in different places in systems. Okay, let me give you one example, two examples of how we can take advantage of 3D stacked logic and memory. I think there needs to be more development in this area. This is a relatively old work from 2012, 2013 that we started. At the time, we were very interested in looking at 3D stacking technologies, logic and memory layers on top of each other. If you have a logic layer that's underneath memory layers that has low latency, high bandwidth, reasonably low energy access, then you can put computation in the logic layer. And you can put any computation as long as you are satisfying area and thermal constraints. And there are other true three-dimensional technologies that are under development that are actually very interesting to me, like monolithic three-dimensional technologies that we have actually some work on, but I'm not going to talk about that right now. So what we did at the time was actually look at graph processing, because graph processing is very intensive. It really exercises this memory bottleneck because it has a lot of random memory accesses and it doesn't have enough computation to overcome those memory accesses. So both performance and energy is affected and scalability is affected. And we wanted to essentially have a graph processing accelerator that is composed of these three-dimensional chips. So I'll call this a cube. Inside this cube, in the logic layer, we have a bunch of processors that are added, a simple in-order cores. And these in-order cores can communicate with each other through a network. And to be able to scale the system, we have a distributed system of these cubes, if you will. And these distributed system of cubes could enable very large graphs or machine learning to be housed in this accelerator. And the idea over here is you partition your graph, partition your data to the memory layers on top of each core. And each core owns that data partition that it has. And whenever you want to do an operation, you don't move the data to the function that's executing on the core. Instead, you send a message to the core that houses the data to execute the function on that data. Essentially, we're moving functions as opposed to moving data. And we kind of took a kind of an extreme stance. We always move the functions, but there could be some middle ground over here. But even with that extreme stance, essentially, we're doing remote procedure calls-based programming. And this, you could think of this as a primitive GPU that's based on near memory processing engines that look like this. If you have a graph processing problem, you can just offload your graph processing problem over here and forget about it. And this PIM GPU kind of executes it and returns the results back. You can think of it that way. Okay, so we have remote procedure call-based programming, and we have some prefetching mechanisms that I'm not going to talk about. And we evaluated this compared to the best systems of the day at the time. And you can see the bandwidth limitations. These are both, these systems have the processor-memory dichotomy. And this is our system, which doesn't have processor and memory separate from each other because processor and memory are integrated with each other, except you have a distributed system of that thing. And we see at the time we had 8 terabytes per second access to memory with 512 in-order cores. And the results were quite good. Essentially, we saw more than an order of magnitude improvement. If you actually do prefetching carefully, you get about 13 to 14x improvement on average across 5 graph processing algorithms. That's good. Later works actually improved this to about 100x or so that I'm not going to talk about. And you can actually reduce the energy also significantly by about 8x. Again, later works built on this and improved it to about 100x. So I think we need to look at these things going into the future for large machine learning models also. I believe there's a lot of processing potential over here. And that's the paper. This was invited as a short retrospective to 50 years of ISCA. If you're interested in reading a 2-page paper, you can look at that. So we also looked at other stuff that I'm not going to talk about, but you can actually expand and get even better benefits on other applications like graph pattern mining. What I will talk about is accelerating neural network inference very quickly before I move to processing using memory. This is the work that I mentioned that we did with Google. And very quick summary, essentially we analyzed the cutting-edge machine learning models that are used in edge machine learning accelerators at Google at the time. And we found out that the edge TPU that's specifically designed for accelerating machine learning tasks, it's a systolic array-based accelerator, essentially is memory-bound. It doesn't handle memory access as well. Because it has this data moment bottleneck, as we have shown earlier. And one of the issues is different layers require different treatment. Some of them are actually very compute intensive, and maybe should be executed in the compute processor-centric system. Some of them are extremely data intensive, and computation is not as big of a bottleneck, and maybe they should be executed on the memory-centric accelerator. So we provide a framework over here, which actually has heterogeneity in the accelerators. And we show in the end that you can improve both performance and energy by about 3x, and also reduce the area consumption. I'm going to talk about that very briefly, but you can actually improve performance, energy, as well as reduce the area footprint. This doesn't mean that complexity reduces. Complexity increases, but a lot of the other metrics reduce significantly. So I think we need to think about solutions like this going into the future. Instead of designing monolithic, single processor-centric accelerators that are huge and maybe not area efficient, designing multiple accelerators that are smaller, but overall much more area efficient can also improve performance and energy efficiency. So let me go through this relatively quickly. Essentially, we analyzed a bunch of different interesting neural networks at the time. And we classified them, and we found out that there's a huge variation in terms of layer characteristics. These are model layer characteristics across the different models. Some layers are actually very intensive in terms of their footprint, as well as very low intensity in terms of their arithmetic intensity. That's flops per byte on the y-axis. Some layers have huge flops per byte and very little memory footprint, as you can see. So designing a single accelerator to cater to this side, as well as this side, is probably not a good idea. And that was the idea over here. And if you look at within a model, even within each model, these are some CNNs at the time, layers exhibit very different types of intensities in terms of operational intensity, as well as multiply and accumulate instructions. So the variation is about 200x or so. Again, it's very difficult to design an accelerator that would cater to this side as well as this side at the same time. So basically, the idea is very simple after this. Instead of designing a single monolithic accelerator that's it tends to be huge to try to cater for everything, we designed 3 types of accelerators. In this particular case, it was 3. And one of them is similar to the processor-centric accelerator, but much smaller, simpler, because it's catering to a very small fraction of the layers. 2 of them are more memory-centric. They're on the logic layer of 3D stacked DRAM, and they're customized for different data flow patterns. And I'm not going to go through this in detail. So how do you identify layer families become an issue over here? We had a profiling mechanism. Actually, I should go back to the previous slide. Essentially, you need to design a runtime that identifies which layer should go to which accelerator. And that's an important area to research, I think, going into the future. So we identify layer families based on these characteristics. Some families have low parameter footprint, high data reuse, and high multiply and accumulate intensity. They go to compute-centric layers. Other families are much more data intensive, and as a result, they're classified as data-centric layers and execute on the data-centric processors. There's a lot more detail in the paper, but the results essentially are significant in my opinion. You can reduce energy consumption by about 3x without a lot of optimization compared to baseline HTPU. You can say that, oh, if I use a baseline HTPU at the time used LPDDR. If you actually use HBM, you can reduce energy consumption, but not too much. So those are the first 2 bars. That's the HBM benefit in energy. HBM helps your performance a lot more than your energy. But if you do processing near memory, you get a lot more reduction in terms of energy. Okay, this is performance. Again, compared to the baseline, we improve throughput significantly. The latency results are in the paper, but you can also improve latency. So I think going forward, we need to think this way. How do we employ data-centric accelerators in our system, and how do we integrate them better so that we can actually hopefully improve overall all metrics? Okay, there's more that we have done in this area that I'm not going to bore you with. I'm quite excited about actually pushing things further into the storage and sensor sides as well. We've been looking at genomics, for example. These are huge data sets. They don't even fit in memory in many cases. And even if they fit in memory, you actually have a lot of data moment to begin with. So we have some works in this area that I'm not going to talk about. And our still to be updated long paper on arXiv that talks about processing in memory has a lot more of these examples. So I could give you more examples, but I'm going to switch to the other type of processing using memory for the rest of the talk. This is a good place to ask a question if anyone has questions, but we could also take it at the end. Okay, at the end. So now we're going to switch to a totally different way of doing processing in memory, which is exploiting the analog operational properties of memory devices. You could do this with any memory device, in my opinion. You just need to understand your device. I'm going to talk about DRAM, because I think it's very interesting. And if you can actually do it in widespread scale in DRAM, you could immediately affect more than 95% of the market of main memory. Maybe more than 95%, I don't know. But it's at least 95%. So basically, this is one slide summary. If you use the analog operational properties of DRAM, you can support many functions. You can support bulk bitwise operations like AND or NOT majority. Essentially, you're functionally complete. You can do copying and initialization, which are actually quite important in my opinion, and we should probably start with simple things like that. You can do true random number generation, physical unclonable function, and you can also do more complex computation using lookup tables if you're willing to pay more. At low cost in general, except for the lookup tables that may be at higher cost, using analog computation capability of DRAM. The key idea in many of these things is to activate multiple rows concurrently or sequentially. And I'm going to give you examples. And what is fascinating to me is, even in commodity off-the-shelf DRAM chips, you can do it. DRAM chips are not designed for this purpose. Manufacturers design it so that you can read or write data. But you can, by violating the timing parameters, you can see that all of these functions are possible. Well, except for the lookup tables that I'm not going to talk about today. And you get significant performance energy improvements by doing so. Okay, let's start simple. Essentially, I'm not going to start with computation, but I'm going to start with another pain point in systems, which is data copy and initialization. This actually happens a lot. In a lot of different applications that I'm not going to talk about, for security purposes, in operating systems, etc. And Google, in their paper that I mentioned earlier, showed that approximately 5% of execution time in all of their data center workload is spent on those two functions, memmove and memcopy. I think this is fascinating. Okay, so how do we do copying today? Essentially, if you want to copy a source page, a white page, to a gray page, you go through the processor. Because we're processor-centric, right? We don't know what else to do. At least you go through the memory controller by doing the DMA. But why don't we just do this? And maybe if you show this picture to a 5-year-old, 10-year-old, they will tell you that, why don't you just do this, right? That's the thinking we need to have in our systems, basically, blank slate thinking, so that we can be much more sustainable. So if you just go do it inside the memory without disturbing the memory bus, processor, etc., this will be low latency, low bandwidth utilization, no cache pollution over here, no unwanted data movement. I'm going to show you a mechanism that takes a 4 kilobyte page copy from 1,000 nanoseconds to about 90 nanoseconds, and 3.6 microjoules to 0.04 microjoules. And if you optimize it, it can be even better. And the idea is very simple. If the source and destination pages are allocated in the same DRAM subarray, which requires changes to the higher level of the stack, which is in general an issue as we will discuss in processing in memory, assume that that's the case. You first activate the source row, which brings the data into the row buffer, which are the sense amplifiers. Now the data is strong over there, and you activate the destination row in quick succession, which connects the sense amplifiers to the destination row. By basically doing two activates, you have copied the data from the source row to the sense amplifiers and sense amplifiers to the destination row. Yes, you move the data a little bit, but it's much better than what we do today. And you're doing it in parallel across, let's say, 8 kilobytes or 16 kilobytes. And there could be other issues, as you can see over here, which I'm not going to get into right now. This negligible hardware cost. And this way you can accelerate things by more than an order of magnitude and close to 2 orders of magnitude energy efficiency in the DRAM. Forget about these bars over here. These bars are the bars at the time we envisioned where you move the data across different banks, across different subarrays, etc. There are a lot of improvements that you can make by slightly changing the DRAM chip to actually reduce these bars significantly also. Basically, the efficiency and performance you get depends on where the data is, source and destination rows are. Okay, so that's the paper in 2013. And let's talk about computation a little bit. How do you do computation? I'm going to talk about real DRAM chips soon. Essentially, you can do this, you can do this in real DRAM chips with almost perfect accuracy by violating the timing parameters. I'm going to show you some results, 99.98% accuracy. That's easier. The harder part is this, essentially it's computation. So how do you do computation? These are 3 DRAM rows over here, A, B, C. I'm showing you only 1 bit and 1 bit line and 1 sense amplifier over here. But imagine this row being 8 kilobytes. What we're going to do is do some operation on these rows that will concurrently operate on all of those 8 kilobytes. And if you actually imagine all of your DRAM to be a computational substrate, and if you supply enough power to it, as you would to a processor, because processing takes power, then all of your subarrays in DRAM, let's say 1,000 of them, may be doing this. So you may actually be doing this concurrently on 10 million bits or more. So the idea is very simple. You concurrently activate these 3 rows. And if you do that based on circuit principles, operational principles, if at least 2 of these cells are charged, those are the capacitors, the final state should be the charge state at the top of the sense amplifier. If at least 2 of these cells are discharged, the final state should be the discharge state. So this is a bitwise majority function, which is a beautiful function. You can try to convert your programs to bitwise majority. You will not be successful because this is missing something, which is a not. But not is already over there. So I'm going to talk about that also soon. But basically, bitwise majority can be rewritten as if you take set C to be 1, you get the OR of A and B. If you set C to be 0, you get the AND of A and B. Now we have AND, OR, bitwise majority. Not is already here. If you activate 1 row, you get the you essentially get the complement over here on the other end of the sense amplifier, because this is a cross-coupled inverter, right? So you can actually supply it somewhere or supply it to the next subarray, etc. But assume that you can do this, which we discussed in our paper. There are some applications that are really good fits. For example, databases. Databases use a lot of bitmap indices. In fact, people have designed databases like bitweaving database to do a lot of bitwise operations. People have designed web search engines to be similar. There are a bunch of other algorithms, like set operations are actually quite interesting. You can express all of your graph mining, for example, in terms of sets. I actually very quickly flashed a paper where we did that in Micro 2021. And this would be very amenable to this sort of acceleration. So you rewrite your program or actually use the program that's designed, which is what we did in this case. And we saw significant performance improvements on database in this case, which is, I think, fascinating. And there has been more improvement over here. This is the original paper that talks about it. We later designed a framework to make this much more general purpose. And the idea over here is user can design any operation. This could be a convolution, this could be a matrix multiplication, this could be a very complex operation like division, or it could be simple operations like, I don't know, max determination, etc. They express it with AND or NOT logic. We convert it to majority inverter graphs, and using electronic design automation tools, we optimize that graph. And then we implement that graph using DRAM commands. This is our microprogram. So you can say matrix vector multiplication converted to DRAM commands across many, many rows. And we store that instruction store the microprogram associated with the instruction in memory. When the programmer calls that instruction in the program, that during execution, that instruction gets shipped to the memory controller, and memory controller executes the microprogram. This way, you can execute anything, essentially. And I think ISAs need to be more flexible going into the future so that you can accommodate new instructions. That's another pain point, I think, in architecture going into the future. And we show that you can actually improve performance and energy compared to state-of-the-art CPUs and GPUs using this approach. I'm not going to go through this in detail. This is the SIMDRAM. More recently, earlier this year, we showed that there are better ways of doing this by actually doing different operations in different subarrays and reducing the width of the vector that you can operate on. But I think this is fascinating. I can talk about that more, but let me switch to what we can do. Sometimes when I give this talk, people look at me in a weird way and say, what are you talking about? Nobody will ever do this. In fact, that was the first comment we received in one of the conferences that we submitted to. The comment was very subjective. DRAM manufacturers will never implement this. And then reject. The paper was rejected. This paper was rejected 4 times before it was accepted, the Ambit paper. But we said that, okay, let's see if it's actually possible in existing DRAM chips. DRAM manufacturers did not do this clearly, but can we do it by doing something different with DRAM? And we actually found out that existing DRAM chips are very capable already. So we designed this infrastructure, PyDRAM, processing in DRAM, essentially to understand the end-to-end benefits. Here we can test end-to-end row clone and true random number generation. I'll give you the picture of the infrastructure. Basically, this RISC-V processor, which is a very simple processor, can execute essentially any program if you put a lot of effort, enough effort into it. While it's executing a program, if it gets to a page copy, this page copy can be shipped to the memory controller, and the memory controller violates the timing parameters to mimic consecutive activates in the same subarray. This requires effort because source and destination pages should be mapped to the same subarray, and we actually do the plumbing to enable that. And we can actually test real programs running on real DRAM, violating the timing parameters and doing the page copy on the DRAM side. And this works. We'd be happy to support it. People can download it. It's all open source, etc. And these are real results from some programs, initialization and copy benchmarks, micro benchmarks. And we see huge improvements. The reason we see huge improvements over here compared to earlier is because the processor that we have, and the RISC-V core over here that we have is really wimpy. It's like 50 megahertz or something. It doesn't have a lot of techniques to overcome the data movement bottleneck. But even if you overcome that, eventually these numbers will reduce, but still they're pretty high. Okay, so this is an end-to-end system. You can actually test it, which is fascinating. You can also do random number generation. You can ship the random number generation function to the memory controller, which violates the timing parameters and generates random numbers, as I will very briefly talk about. So you can say, okay, this is interesting. What about computation? So more recently, again, this year, we've shown that existing DRAM chips can actually do computation. I'm going to give you some results. This is a very quick summary. Well, the first one is not computation, but I already said that. Essentially, in existing DRAM chips, you can copy one row into up to 31 other rows with almost perfect success rate, 99.98. We're working on the 0.02, but there are some applications that could benefit from this already, in my opinion. You can perform the NOT operation without changing DRAM chips. Again, with up to 32 output operands. You can perform up to 16 input AND, NAND, OR, and NOR operations, again, without changing the DRAM chips. The DRAM chip is the same, interface is the same, you just design your memory controller and violate the timing parameters. So I'm going to give you a couple of examples. NOT operation I've already kind of alluded to. Essentially, you have a NOT gate. If you have a subarray, in open bit line DRAM architecture, you have a subarray on the top and subarray on the bottom that are connected to the same sense amplifier. What you can do is you can connect rows and neighboring subarrays through this NOT gate by simultaneously or very quickly consecutively activating rows. You first activate the source row, which essentially starts the sensing process over here, and you quickly activate the destination row. And while you do that, while this is being sensed, you get the complement of 8 over here. And we essentially see this quite reliable. How do you do NAND, NOR, AND, and OR? I'll give you the basic idea. Actually, you can implement any function, as long as you know what you're doing. If you think about a subarray, 2 subarrays over here, you have 2 rows over here, AB, 2 rows over here, XY. We have a way of concurrently activating all of them. Essentially, we have figured out that by violating the timing parameters, all of these can be concurrently activated. Now, if you do that, this is called multiple row activation primitive. If all of them are concurrently activated based on circuit principles, what you have over here is the average voltage of A and B, and what you have over here is the average voltage of X and Y. And what the sense amplifier senses, it compares the average of A and B to average X and Y. Now, you can implement any function by manipulating A and B carefully, and there's a way to do that in real DRAM chips. And this way, you can actually get AND and OR. I have actually a demonstration of how you actually get AND and OR, but we don't have time to go over that. So we tested this in our DRAM infrastructure from multiple manufacturers, and we find out that essentially commodity off-the-shelf DRAM chips can perform these operations. They can also perform these operations quite reliably, 94% success rate, which is clearly not perfect, but DRAM chips were not designed for this. This is fascinating because if DRAM chips were not designed for this, and we actually are able to uncover this functionality, think about what we could do with DRAM if you actually go and design the chip for this purpose. Go and figure out how to design the row decoder. Go and figure out how to design the sense amplifier. Yes, these are core areas that no one wants to touch. But if you don't touch anything, you don't get any benefit. Okay, so this is the paper that talks about that. So what else can you do? Very quickly, as I said, you can generate random numbers. Again, in real DRAM chips by violating the timing parameter. The idea is you activate one row, and when you activate the row, you don't wait for the sense amplifiers to settle. And if you actually give some time, some cells fail randomly. These are random number generator cells, and you can use them to generate random numbers at high throughput, low latency, low energy. There are better mechanisms to do that. In fact, we have even better mechanisms coming up that we will talk about later. You need to do end-to-end design to enable this. You can do physical unclonable functions, which I'm not going to talk about, and you can do lookup tables also. You can do all of these things in Flash as well, which I'm not going to talk about. We've demonstrated all of these things in Flash as well, in real Flash chips and with perfect reliability in this particular case, because we have a controller that enables us to figure out, that enables us to set the voltages so that when you do computation, those voltages don't overlap with each other. Okay, so I've covered both directions. I'll cover something that's, you can find a lot more in our paper, but now I'll talk about something quickly that's maybe even more important, which is really adoption, right? We can talk about all of these interesting things, and it's fascinating that we're discovering these functions in commodity memories today. How do you get these adopted? As I said, I think processing near memory is easier to get adopted than processing using memory, but I think we should work on both. In my opinion, there are a lot of challenges, and all of those challenges, almost all of those challenges relate to system and software. We need to figure out application of software, and I believe machine learning is one example, but there are many other examples too. But we need to show benefits. I think this is already happening. The evidence is growing, in a sense, for a potential paradigm shift. Ease of programming is extremely important. I'm going to briefly talk about that, but not give you a whole lot of things. I'd be happy to talk about it separately. We need to ease the programming for everybody as much as possible. We need to provide system and security support, coherence, synchronization, virtual memory, some things that are very hairy in processor-centric systems. We already have all of that hairiness, and this is going to get even more hairy if you actually port it to the processing near memory systems. Runtime and compilation systems to make the programming tasks easier and the system tasks easier, and also infrastructures to understand how we can more fairly and better evaluate this. I think all of these are solvable, but we need to really change our mindset to a more data-centric mindset, right? If we start with processor-centric mindset and say, oh, data mapping, for example, I'll pick that one, that's my favorite. The data mapping today is not good for processing in memory, so let's stop and let's not do it. That's not going to work. You need to change the data mapping, because data mapping is today processor-centric. Every single decision we make in our systems today is processor-centric. We need to revisit all of them. Okay. So I think I've already said this, but we need to revisit the entire stack also. I'll very quickly talk about programmability. We have more works in this area. Compilation support is really important, I think. We've tried to, for example, to have compilation support to transparently map applications to processing in memory. But I think in the end, you need to change the programming paradigm slightly, at least. And we have been working on data parallel frameworks for processing in memory. We actually have this paper, SimplePIM, which is a higher level framework for software that could, I think, be implemented better with existing processing in memory systems. We have tools to enable this to be better, and we have ways of considering different things that I'm not going to talk about. Coherence is important. We've been working on that also. Synchronization is important. Virtual memory is important. And most importantly, I think to enable all of these, we really need to work on infrastructures, and we have a bunch of infrastructures that I'd be happy to talk about. Okay, now let me conclude and I'll take questions. So I think going forward, we want sustainable architectures, which requires energy efficiency. For that, we need data-centric architectures, I think. For high performance, we also need data-centric. And for high security, high robustness, we also need data-centric. I should put that in my slides going forward, I think. I think we need to design architectures with minimal data moment. I think I already said a lot of these, but we need to design systems to be balanced. Today, we're breaking that balance, meaning we're moving all the data through processor. There's no balance in our systems. So when I teach the digital design class, which I do every semester to 600 people, I say a fundamental principle in architecture or digital design is balanced system design. And then I'm ashamed to present very quickly a processor-centric design, because that fundamentally breaks the balance. And I acknowledge that to the students. I say that this is the state of the art. You can change the future. Okay, so we need to be data-centric, I think. So I think we need to enable computation capability inside and close to memory. This can lead to orders of magnitude improvements. I've shown you some examples of this. There are a lot more examples in the literature. I believe this can enable new applications and computing platforms. This is fascinating, I think, especially on the edge, but also maybe in the larger scale as well. This can enable better understanding of nature as well. I think especially you try to do more analog computation integrated with memory. And who knows what else. The future is bright, I think. But we still have a lot of hard work to do to get this to be a very, let's say, prominent paradigm. But I think the benefits that will ensue will be huge also. Okay, I'll leave you with kind of this picture. I think it's good to think about whether this picture is actually a processor-centric picture. I don't think so. I don't claim to know everything about it. Okay, So I'll acknowledge some people. We have all the papers, talks, and artifacts on our website as well as GitHub. We have funding, thanks to EFCL, for example, and other folks. And most importantly, I'll acknowledge people who've done the work. This is my group of students, postdocs, collaborators, and you can find some information about them in our newsletters. And we also give PIM tutorials. The last one happened in November 2nd. And Micro, if you're interested, you can actually watch it. And feel free to send us comments, questions, and we'd be happy to collaborate. I'll stop here. I'm happy to take questions.
Okay, thank you very much, Onur, for the very nice, fascinating talk. Any question for the, yeah? Maybe we need, because there is people on the line, yeah.
Sure.
Mohammad Alian, Cornell. So you talked about starting from clean slate. If you are about to design a new DRAM architecture, do you do some makeshift changes in the current DRAM architecture? What do you do? I mean, what would be the...
Yeah, that's a great question. I think ideally we should start from the clean slate, but I think, so research should be very heterogeneous, in my opinion. There should be some research that's more incremental changes to DRAM, and then there should be some research that's basically clean slate DRAM. I don't see this clean slate DRAM research happening as much. I'm guilty of that also. But I think we need to do more of that also. Like if you have to redesign a DRAM architecture or some other memory architecture completely from the ground up to be data-centric, to overcome all of those issues, how do you do that? I think that's a great question to ask. I would do that, but I will also do the other part, which is more incremental, because it's so that you can actually get things maybe married in the middle at some point. Who knows?
Onur, great talk as usual. About the DRAM work, it's really fascinating, but I mean, so far, like all the experimental validation that you have done, you are kind of violating the timing constraints and playing tricks with it, right? So have you started working with some DRAM vendors to really do it in the circuit level?
Yeah, that's a great question. So actually, we don't directly work with them at this point, but they're actually very interested. Multiple vendors reached out to us and they said, this is very fascinating. They didn't think that DRAM was capable of this. So they're actually investigating internally what they can do. I still think it'll be some time because, you know, there's a mindset in DRAM and in general memory companies that's not very...
low risk.
Exactly, you know, low risk and other issues also. But the fact that they actually are interested and they try to replicate this, they try to simulate it internally, and they try to do things is, I think, good news from my perspective. We're happy to work with them, but, you know, sometimes they have constraints that are not, let's say, well aligned with academic pursuits.
Sure. Yeah, thanks.
Thank you, Professor. In the presentation, we know that the data-centric design has a lot of advantage in terms of performance and energy efficiency. And I just want to ask, is there any disadvantages of the data-centric design? And yeah, that's my question. Thank you.
Yeah, that's a great question. I mean, absolutely. Like any idea, there's always advantage and disadvantage. Everything's a trade-off in the end. What is needed for, I mean, in general, I'm talking about in general, in data-centric paradigm, clearly it will increase complexity, right? Your memory will become more complex, your system will become more complex, at least initially. Over time, overall complexity may reduce because you may actually take out some of the complexity that's added to a processor today. But initially, there will be some complexity increase. And also a complexity increase will not just be in the hardware side, but also in the software side, right? You will need to decide what to execute where. Should I execute in the processor, GPU? Now we have one more place, or maybe multiple more places, if you actually enable computation capability in other places. So there needs to be, I think the major issue, in my opinion, is complexity and programming, and all the adoption issues over there. But if they're, over time, in my opinion, they can be solved. In a sense, all of these issues existed even in the processor-centric paradigm when we had the, let's say, difficult transition to heterogeneous accelerators, right? If you look at how people do heterogeneous acceleration today, even GPUs, right? GPUs existed and people started using it, and they went through the pain of mapping their applications to GPUs. Now we have machine learning accelerators, clearly for good reason, But all of those machine learning accelerators require the software stack to change. So I think data-centric paradigm essentially puts it in a different place, but the challenges are not that different, in my opinion.
Hi, Suleiman here from Huawei. A bit of philosophical question here. So what do you think the computer architecture will look like in a bit far future? Will we have only some memory chips with the logic in them, or will we have some conventional architectures going in the future?
I think that it will be heterogeneous. Meaning there are things that we can do in a processor that we really cannot do in memory technologies, like extremely high speed logic with high complexity. I don't think it's going to be as easy to do that in any memory technology going into the future. Analog computation we can do, but we can also perhaps do analog computation in the CPU. Yeah, I think it'll be really heterogeneous. We will still have. I don't think we will get rid of the processor. We'll have a lot of heterogeneity. But my hope in the much longer term future, I don't know when, is you really have all of these collection of very different types of processing elements. Some of them are data-centric, some of them are processor-centric. They're all potentially specialized, or they could be reconfigurable. But they're all equal agents in the sense that you send your computation, and it's a distributed computation, and the computation happens without a central processing unit managing it. So it really happens, let's say, in a distributed manner. Maybe somehow, yeah. I'll not go into that more detail, but that's not what I talked about. What I talked about was more still accelerator-based computation, right? We use like data-centric computing for acceleration.
Very little question.
Okay. Sure. Sure. Yeah.
Hi, I'm Nirban from Huawei. So I have a question. So in the beginning, you showed two different pictures of lush green field, and then multiple chimneys spitting out smoke. And you spoke about sustainable computing, and your idea of the talk was to improve energy efficiency. But as I understand correctly, a lot of carbon emissions come from actually manufacturing these devices, right? And a big aspect of sustainability would be to improve the lifetime of these devices. Now, what do you think of the case where doing these multiple row activations for in-memory or processing using memory, does it affect the lifetime of these devices, and does it work against the sustainability goal?
Yeah, I think, okay. I think there are two questions here. One is, how does this affect sustainability, which is a very complex question in my opinion. And the second is, if you actually look at these multiple row activations, how does that affect lifetime, reliability, robustness? I think the second one is a lot easier to answer. I'm going to try to stay away from this, but it's very hard. The second one is easier to answer, and we actually have looking at that, like especially robustness issues for these analog type of operations. And I think there are some fascinating discoveries to be made over there. The first one, in terms of sustainability, I don't think it's just about lifetime, right? It's also about the cost of a system. And I think it's very difficult to quantify. That's why I didn't want to get into a lot of that. For example, today in our systems, because of the way we're designing our paradigm, our processors, in my opinion, we have huge hardware, right? Maybe if you move to this sort of paradigm, you get rid of the hardware, right? For example, in the Google work that I mentioned, the edge neural networks model work, we've shown that you can reduce the hardware cost by about 40%, 30% by designing 3 accelerators as opposed to 1. So maybe that has an effect on sustainability. I cannot exactly quantify it. I'm not sure if there's any model out there to be able to quantify it. But I believe this sort of thinking and paradigm shift can enable much leaner hardware and less hardware as well, if we actually try to optimize for that goal. Hopefully that answers your question.
Okay, so thank you again, Onur, for the very nice talk. And I think we can move to the coffee break for half an hour. Actually, we start back at 10:30. And maybe just for the next 3 industry speakers. So in the next session, we have industry speakers and panel. Maybe if we can just be sure that your presentation is uploaded and we can try, I think during the break, it's the best. Okay, so thank you again, Onur. and see you at 10:30.